Hello and welcome to lecture 16 of the course Theory of Computation. So far in the course we have seen regular languages, we have seen how they are represented. So we saw DFAs, NFAs, regular expressions. We saw pumping lemma which gave us a way to show how languages are not regular. We also saw Myhill-Nerud theorem. So now in this lecture we are going to start on a new topic which corresponds to chapter 2 in the book called context free languages, right? So this is we can consider this as the next step from the regular languages, right? So this will be somewhat more general than regular languages, and one of the applications will be that it is useful in let's say compilers or parsing languages, right? So for regular languages, we had 2 or 3 ways to represent them, right? So one was using DFAs or NFAs, and one was using regular expressions, right? So DFAs and NFAs were basically a machine-based model, right? So we had an automata in either case, and whereas regular expressions was like an expression that needs to be interpreted into a string, right? And you could do that in multiple ways. Similarly, in the case of context-free languages also, we will see the same similar situation. We will have one machine-based model which is called PDA. Okay, so PDA stands for push down automaton, and we will see something like regular expressions called context-free grammar. So grammar-based representation, right? So in regular languages we had 2 machine-based representations, whereas in context-free languages we will only see one called push-down automaton, right? But in the case of context-free languages, we will first see the grammar-based representation called context-free grammar. So the class of all languages that can be represented by context-free grammars is going to be called context-free languages. Later we will see the other representation also. We will also show the equivalence. But first we will start with context-free grammars, right? So as I said already, it is more general than regular languages and have more interesting applications. So we can do more things with context-free languages, right? So let's start. So what are context-free grammars? So basically we have some variables and we have rules to interpret these variables, right? So here in the left side we have these 3 rules. One is that A right arrow 0 A1, then A right arrow B, then B right arrow small b, right? So we can think of the right arrow as a rule of a substitution rule or a production rule. So A yields 0 A1, or A yields B, or B yields small b, right? So what this means is that we can in a certain situation we can replace A with 0 A1, or we can replace A with capital B, or we can replace B with capital B, right? And typically there will be 2 kinds of objects that we will deal with. One is denoted by capital letters, capital A and capital B, called variables, right? So typically capital letters. So in this example it is just A and B. And 2 is terminals. So in this example there are 3 terminals, 0, 1 and B. So small letters, numbers and maybe other symbols also sometimes. These denote terminals. So terminals means that you cannot further substitute them with other things, whereas variables are variables, so there are ways to substitute them. So here A is a variable, capital A is a variable. There are 2 different ways to substitute them, right? So you could replace A with 0 A1, or you can replace A with B, right? Whereas once you have small b, then you cannot replace them, or you have 0 or 1, you cannot replace them with anything else, right? So a variable needs to be replaced, and till you get a terminal. So let us see what all we get from this grammar, right? So let's try to see some examples. So one is that A yields 0 A1. And now let's say or maybe I'll use another one. So A also gives us B, small capital B, and capital B gives us small b. So now small b cannot be, you cannot do anything with small b because it is a terminal. Another possibility is A yields 0 A1. Now 0 and A and 0 and 1 are terminals, but A you can again replace it with B, and B again you can replace it with small b. Now another way to do it is A gives us 0 A1. Now we can again use the same rule to replace this A, right? To replace the underlined A, we can again use 0 A1, right? So this underlined A was replaced with 0 A1, and now let me say I have 0 0 A11, so I am replacing it with a small b, capital B, and then capital B with a small b. I can do this any number of times. So A gives 0 A1. Now this A gives 0 A1 again, and this A again gives 0 A1, and now So these are all strings that can be obtained. So notice the strings, that the ending strings that we have. So the first case it was B, then it was 0 B1, then 0 0 B11, and then 0 0 0 B111, right? So and now you may kind of see the pattern here, right? So strings generated are, and are B 0 1 0 B 0 B1, 0 0 B11, 0 0 0 B111, and you can see the pattern here, right? And you can also convince yourself that these are pretty much all the strings that are generated look like this, right? So B and then some zeros before B and some ones after B, where the number of zeros and number of ones are the same, right? So these are the kind of strings that are generated by this particular grammar. And so now once we reach some string like this, let's say we reach 0 0 B11, right? So now we cannot do any replacement, because 0 0 B11, each one of them, the three terminals here, 0 B and 1, right? 0 appears twice, 1 appears twice. But these are terminals, meaning you cannot replace them with something else, right? You can only replace a variable. A variable in this case, there are two variables A and B. A and B, capital A and capital B can be replaced, but small b and 0 and 1 cannot be replaced, right? So the goal, even though I not formally defined it, I hope the goal is now clear. To get a string, we need to start with A, okay? So why A? I'll just very soon tell you. So you look at the first. So I have written three rules here, right? So there is 1, there is 2. So this is rule number 1, this is rule number 2, and this is rule number 3. So you look at the rule, the first rule, and see what is the variable that is replaced. The first rule, the variable that is replaced is A, right? The variable that is on the left side of the rule. So the rule is one variable and what to replace that variable with, right? So the variable can be replaced by another variable. It could be replaced by one terminal. It could be replaced by two terminals, or it could be replaced by two variables, or a string of multiple variables and terminals, right? A combination, right? Could be any of these. So you look at the first rule and the variable on the left side of that rule, left hand side of that rule. That is the starting variable. Now you start with the starting variable and you get to some string that is entirely composed of terminals, and that is a string that is generated from the language. So in this case we saw multiple strings, and you can get even more strings. In fact, there are infinite strings that can be generated, right? So again, I've written it in detail here. So the start variable is on the left hand side of the first rule. So what you have to do is to start from the start variable and repeatedly replace the variables. You repeatedly replace the variables in the resulting strings with using the rules, and you repeat, like how many times you have to do this? you have to do this till there are no more variables, right? So in this case, there are like these, like we reach these strings, the underlined strings, right? So there are and when we reach them, there are no more variables, right? So this is the goal, and we'll state it a bit more formally a bit further, but this is this is how you get a string from a grammar, right? So you start from the start variable and you repeatedly replace a variable with a using a rule. So here we have three rules: replace a with 0 a1, replace a with capital B, replace capital B with small b, and you do that till you end up with a string that is consisting of only terminals, or completely eliminate variables. You can also draw a thing like this. This is called the parse tree. So this is the tree where we are seeing how 000b111 is derived from A, right? So we start with A, right? We started with this A, and this A yielded 0A1, right? So this the topmost A yielded 0A1, and the second A again yielded 0A1, right? And the third A yet again yielded 0A1. That's how we got 000 to begin with and 111 at the ending. But the fourth A just yielded a B and capital B, and the capital B just yielded a small b, and that's how we got the 000b111. So this is the same derivation, but we are writing it in a tree form, right? So tree form is probably easier to visualize instead of writing repeated derivations, right? And sometimes this is helpful because sometimes you have multiple variables. So in all these constructions that we had here, we just had one variable each time. Sometimes when you have multiple variables, this is easier to visualize, right? So, and you have to replace one after the another in the case of a derivation, but in the case of a tree, you can just visualize them better, right? So this is what this is the context free language, or this is the context free grammar, and how you derive strings from the context free grammar. So let's try to see why this is interesting. Like, what can you do in context free grammar that, for instance, we couldn't do in regular languages, right? So for instance, if you have written any kind of program, or even something like using MATLAB or some kind of thing, like you would know that you need, let's say, when you have writing mathematical expressions, you need properly nested parentheses or brackets, let's say, right? So meaning, let's say, so here I have written a language of brackets, okay? Brackets meaning the square bracket. So set of all strings that are formed just using open square bracket and close square bracket, such that it is properly nested. So what are some examples? So I am just using square brackets instead of this parenthesis, because this is easier to draw and visualize, right? So there is no curves there. So this is, for instance, a string that is properly nested. Here is another one, right? So in the first case, the starting bracket ended here, matched here, and then further there is two nested parentheses, one inside the other. The second case, the starting bracket closed here, and within that there is one nested bracket, and then outside that there is another nested bracket, right? Here is another example. So I'll just match, this matches with this, right? So you can see why they match, right? Maybe I'll just note it down. This 1 matches with this 1, 2 matches with this 2, 3 matches with this 3, and then 4 matches with this 4, right? And you can, so what do I mean by properly nested? Properly nested means that the opening and closing should be in the right order. It should not be that, so for instance, this is not properly nested, right, because the closing comes, so even this, for instance, let's say, even this is not a properly nested language, because not properly nested string, because it doesn't even match. So for being properly nested, we need more than just matching, the number being matching, because so here the number matches. There are 3 open brackets, 3 close brackets, but this is not a properly nested one, because you cannot, there is one closing off and then there is something opening, right. So that is the definition of properly nested, and this we know it is not a regular language. Why is it not a regular language? Let's see why. For instance, let's consider this language, that is just open bracket star and close bracket star, right. So just two, it is just a alphabet of using 2 symbols, that the open bracket and the close bracket, right. So the alphabet here is, right, just these 2 symbols, and the language A that I am writing here, right, I am writing here, this is a regular expression over the alphabet, and clearly because it's a regular expression, it's a regular language. So some open brackets followed by some close brackets, right. So now we had L here, right, and we have A here. What is L intersection A? In other words, what is the set of all properly nested brackets which have the structure of A? So if you think about it, you will see that the only way to be properly nested within the structure of A is to have some number of opening brackets followed by the same number of closing brackets. In other words, it has to be some number of opening brackets followed by the same number of closing brackets, right. So it's like open bracket n times followed by close bracket n times. This is L intersection A. If L was regular, we know A is regular by the regular expression, and hence if L was regular, L intersection A also would have been regular, right. But we know this is L intersection A is not regular, right. We know this because we saw 0 power n, 1 power n when we studied regular languages, and we know 0 power n, 1 power n for the same n is not regular, right. So L intersection A is, and this is the same as 0 power n, 1 power n. It's just that instead of the symbol 0 we have open bracket, and instead of the symbol 1 we have closed bracket, right. So L intersection A is not regular, right. So this is clearly not regular, hence L is not regular. If L was regular, then L intersection A also would have been regular, right. But we can show that L is context free. For instance, we'll soon see a context free grammar that that generates all the bracket pairs which are properly nested, right. So just quickly I wanted to show L intersection A or something like L intersection A, right, similar to L intersection A language. So let's say B is just 0 power n, 1 power n. It is the same as L intersection A, but instead of 0 and instead of open bracket we have 0, and instead of closed bracket we have 1. The following the grammar in the box, this works. This generates, this grammar generates B. So you can see why it generates B, for instance. So you start with S because that is the only variable here, right? And then you can use, for instance, there are two things that you can do. You can replace S with empty string, in which case you have a string, or you can replace S with, let's say, 0 S1, maybe this S again with 0 S1, and then maybe with empty string. So you can see the strings that you generate are of the form 0 power n, 1 power n, right. So this B is context free, whereas meaning this is a context free language, meaning there is a context free grammar that generates this language, whereas we know it is not regular, right. So already we have seen example, or this is an example of a language that is not regular but is a context free language. And this is not the first time you are hearing the word grammar, right. So the word grammar you might have heard while learning languages in school, English or any other like Hindi or any other local languages that you might have heard or learnt, right. So we have grammar. So basically what is grammar? Grammar is just a bunch of rules as to how you structure your sentences, how you put together words to form meanings, right. There are certain rules of what should go with what and how they should connect together, etc., how to form sentences. The grammar in English is not the same as the grammar in an Indian language, right. So every language has its own specific set of rules, and that is the grammar, right. So even for natural languages such as in English, we have the grammar, right. So in fact, there is in the book there is an example of how you construct sentences, simple sentences using things like noun, verb, preposition, adjective, etc. I think in my copy of the book it's in page 101. It's towards the beginning of the chapter 2. Please have a look at this, right. So I'm not rewriting the same example of how you can construct a sentence using these things like noun, verb, adjective, etc. Now let's see some more examples. So here we have a context free grammar. So let me just explain. So there are two variables. One is that S, the other one is A, and in the second line we see these vertical lines, right. So I'm talking about these vertical lines, right. So this means that A can generate this means that A can generate, this is actually three rules. One is that A can generate epsilon, or it can generate small a capital A, or it can generate capital A S capital A, right. So this is three rules. We are just this vertical lines denote or, right. So all it's saying is that there are three rules, we are just writing them together. A can generate this or that, right. The first one, the first line says S generates open bracket, open parenthesis, A close parenthesis, right. So what are the variables here? So the variables here are S and capital A, and terminals here are small a, right, that's a terminal. Empty string is empty string, so that's not a terminal. Then open parenthesis and close parenthesis. There are three terminals here, right, because they are also terminals. So let us see some strings. So S generates, this is the first rule has to be like this, right. Now A, let's see what it can do. Let's say A generates small a, maybe another small a, and maybe let's say A generates ASA, and maybe the first A generates empty string, let's say, and let's say S generates a this, right. Now let's say, I think we are running out of space, so I'll just say, hey, both of the A's, let them generate empty string. We'll just do step by step still. So this is a string that is generated, right? So I'm just every time I am replacing one of the variables here with using a rule with whatever is coming out of that, right? So I got the string open parenthesis a open parenthesis again close parenthesis, right? So this is just one example of a language, and here let's say this maybe I'll just erase this and use a different color for this. So here variables are, there is only one variable s, and terminals are small a small b. Empty string is just empty string, it's not a terminal, right? So here let's see, s gives a s b, maybe once more a s b, and maybe once more a s b, and maybe then we replace it with empty string. So you have a b b b. Another possibility is a s b and then a b, like this. We use the rule s yields the empty string. So here we can see this gives you a power n b power n, right? So you can check that this gives you a power n b power n, right? So derives a power n b power n greater than 0. So this you can check. I'm sorry, I'm a bit cramped here for space, but you can see what I'm doing here, right? So hopefully by now it's clear how you can play around with the context free grammars and the kind of strings that you can generate, right?